In this video, we'll be talking about what a one-to-one function is, as well as the graphs of inverse functions. Now, if you were asked to find the inverse function of this particular equation right here, again, in the last video, we learned that we would take f of x, replace it with y, swap x with y, and solve for the new y, providing us with x plus or minus the square root of x. And the reason why it's plus or minus is, again, every time you take the square root of both sides, you must put a plus or minus on at least one of those sides. Now, the square root of y squared is simply y. The square root of x is going to be the square root of x, again, with the plus or minus. Now, with this, that means that f inverse is supposed to be equal to plus or minus the square root of x. Now, there's an issue with this. This is not actually inherently a singular function. Because of that plus or minus, there is actually two cases that are occurring here. F inverse of x equals to the positive square root of x, or f inverse of x equals to the negative square root of x. And again, notice, in the middle I said or. So that means that I can't select very specifically which one of these two functions would be the inverse of x squared. Now, to help understand this better, let's go ahead and graph the quadratic function, y equals x squared. It'll look something like this. Now, if you were to look at this function, okay, and let's talk about, again, how do we find the inverse? We take the x and the y and we swap their positions. So in reality, I'm going to look at the line that is y equals x. I'm going to draw a dotted line through this point. Now, this is the line y equals x, where this is the function y equals x squared. If I were to take this quadratic and attempt to reflect it over this dotted line, reflecting it over this dotted line is legitimately swapping x and y. So, what I'm going to end up with is something that looks like this. Notice at every location that it crosses the dotted line, it should intersect with the original graph. So here and here it intersects with the original graph. The only unfortunate part is that if you look at this, this is a sideways parabola, a sideways quadratic. But a sideways quadratic is not a function because it doesn't pass the vertical line test. It failing to pass the vertical line test would imply that this is not actually a function. Now, this would be if f inverse of x. However, this right here, this top half, is simply the positive square root of x. Separating it right here, this is f inverse equals to the bottom half. Now, for us to verify that this thing is actually an inverse, we have to restrict the domain of the original function. So, for instance, if in the original problem I said f of x was equal to x squared on x being greater than or equal to 0, that means that I'm on this half of the function, and when I reflect it, it becomes this half of the function. So that means f inverse of x is then restricted to the square root of positive x. This would be the possible solution if I was restricting that domain. Secondly, if I were to take this function and restrict it to be less than or equal to 0, then my f inverse of x is going to be equal to a negative square root of x. Again, on this graph, it would be over here, and this function right here would reflect perfectly over this dotted line into this spot right here. Now, these are potential inverses of the of x squared. Now, you'll notice if I try to work my way backwards, the square root of x, if I'm just looking at this function, then it reflects perfectly onto this function here. And there's no issue. So I could easily say, if I had g of x equals to the square root of x, that g inverse of x is easily equal to x squared. Now, technically, because this thing is only defined on the x values, again, its domain is x being greater than or equal to 0, because that's the domain of a square root function, then this one right here, its range values must be greater than or equal to 0. Again, because we're swapping x and y, the x's in this one become the y's in this one. However, the y's in this one, being y equals greater than or equal to 0, must also imply that the domain of this one down here is x being greater than or equal to 0. So, it's very important to note that a one-to-one function, and this is where we're getting back to that definition, a one-to-one function is simply a function that not only passes the vertical line test, but it must pass the horizontal line test as well. For a function to have an inverse function, it must be a function, and b, must pass the horizontal line test. So in other words, for us to have one-to-one, a function must not only pass the vertical line test, but the horizontal line test as well. So if it can satisfy these characteristics, we can simply create an inverse function and graph that inverse function on a coordinate plane without any interference of the domain restrictions. Now, one other last detail to summarize here is that if we're looking at the domain of f, the domain of f should be equivalent to the range of f inverse. Likewise, the range of f should be equal to the domain of f inverse. Knowing these two details allows us to make a lot of conclusions without having to do a really large excessive amount of work.